guys, and welcome to my webinar presentation. The title is a little bit different than on the lecture slate. It's more here on the improving of a biorefinery output by coupling some biological processes and then doing some fast process or slow process to make some biochar basically. So it's more of talk about how to couple certain processes to get max value out of a biorefinery, all right? This is the context I will present for today. A bioprocess to a thermochemical process. And I have two case studies. One case study is about coupling ethanol fermentation, as well as anaerobic digestion, as well as slow pyrolysis. And this is called digested stillage here. And I also have then a second case study I will present, which only combines anaerobic digestion and slow pyrolysis. Hence, it's called only a digestate, right? Then, to conclude a little bit, I will compare the feedstocks being a digested stillage for pyrolysis and a digestate for pyrolysis. How these two compare in terms of pyrolysis product output, let's say. So as promised, first part on some general aspects, how to combine biological processes and thermochemical processes. Here I have a nice figure. On the right, you can see like a general figure that starts from your biomass, using your biomass being lignocellulosic. Using your biomass being lignocellulosic, apply it for fermentation to convert your carbohydrates to bioethanol. And then afterwards, you would obtain some stillage residue. And that stillage residue find its way to a digester. And you hope in the digester that you would convert your residual cellulose or hemicellulose to biogas. And then you end up with some solid material, which is called the digested sludge. And then afterwards, we perform some pyrolysis to convert that digested sludge to the products. Right? So this is a sequence: fermentation, digestion, and pyrolysis. Why this sequence is kind of interesting? That's because you can valorize each fraction independently from each other. So first you would convert all the cellulose, then you would convert most of your hemicellulose, and afterwards you're able to convert your lignin. So this is the first sequence, and then I have a second sequence, and you can see that I have erased the enethyl fermentation part on the top in the slide. So we only left with the digestion part and the pyrolysis part. So the part in the blue rectangle on the right figure. There it was a goal to co-valorize the cellulose and hemicellulose all at once in one single stage to the biogas, and then have your residue and convert it to the char and oil upon pyrolysis. Right? So these are the two processes I will go more in detail to. First, digested stillage, then the digestate. All right. Here is a figure which makes it more like detailed on how these materials were obtained. You can see in the figure that you start from poplar in one case, being woody biomass, and you do some bisulfite treatment to make the matrix more accessible for the enzymes later on in the simultaneous saccharification fermentation process. And then afterwards, the specs or the conditions for digestion are specified there. You end up with the digestate, a lignin-rich digested stillage from the poplar after these three processes. Then in the second part of the figure below, I hope you can see my mouse here. Yes, my pointer. In this part, you would be able to see that the cocoa pod husks, which was the feedstock used here in this case, were only digested to only result in a digestate, and both the digestates, the stillage digestate and the cocoa digestate, were converted via pyrolysis. So in this part, this is the second part already. I will focus a bit more on the digested stillage part, which has been recently published in Biomass Bioenergy. And you can see there the graphical abstract, which kind of tells it all. You can clearly see there that you start from the lignin-rich digested stillage, you make your biochar, and you assess some properties like elemental properties being the HE ratio and OC ratio. And you try to optimize the process conditions in such a way that you have like a compliant biochar or an optimized biochar, let's say. So we'll talk you through the details of this research. First, I will start with some specs of the lignin-rich digested stillage. The high heating value is about 20, which is, I would say, on the higher end of typical biomasses. I guess a typical biomass is between 80-something, 18-something. We have here 20-something. It might be due because the carbohydrates are already valorized to the ethanol and to the biogas, and your lignin fraction is more energy-rich. Hence, you would expect a slightly higher energy-dense compound here. So hence, the 20s logic has a value. It's also nice to see that you have the elevated lignin content. You check the class on lignin composition being 63. It's already kind of high, which also is the logic because you have tried to valorize the cellulose and hemicellulose already in previous two biological processes. Right, if you don't check the elemental composition, I have a table there on the carbon, hydrogen, nitrogen, sulfur, and oxygen contents. And I have compared the lignin-rich digested stillage with straw as benchmark, let's say. You can actually clearly see that the carbon contents as well as nitrogen and sulfur are higher for the lignin-rich digested stillage compared to your straw. And then on the other hand, you would see that there is less oxygen in the stillage compared to the straw. And this is again revealing or showing that the carbohydrates which are more oxygen rich have already been valorized and gone out of your solid fraction. And therefore your oxygen is lower of your feedstock, right? The sulfur and the nitrogen are introduced by the process itself, let's say. If you have your pretreatment in the first stage, you would notice or remember that there was a bisulfite treatment, and therefore the sulfur in that treatment might have find its fate, let's say, in the solids. So therefore, you can explain the slightly elevated sulfur content. On the other hand, you would see that there's also high nitrogen. This is explained by having these microorganisms in your digester and in your fermentation unit. These microorganisms have proteins, have therefore nitrogen, and therefore you would observe some more nitrogen in your digested stillage compared to a straw, for instance, right? Also, which is nice to see for later perspectives, is that your ash, being your nutrients, is kind of very much higher in your lignin-rich digested stillage compared to the straw. So it's kind of safe to say that throughout all the processes of fermentation, digestion, you are retaining your nutrients, your ash fraction in the solid part. So while valorizing ethanol and having biogas, you keep the ash in the solid phase, and if you would then have a pyrolysis system later on, you would also retain your ash in the biochar, and if you don't put the biochar in soil, you would have like a closed loop for your nutrients inside. However, if you check another property of this feedstock, the lignin-rich digested stillage, this is your TGA. On the left, there is a TGA here. I hope you can see my pointer. There's a TGA of the digested stillage here. And on the right panel, there's a TGA of an organosulf lignin, which is virtually pure lignin. And what is nice to see is that actually the residual mass fraction upon of the complete TGA analysis is like 20-ish for the lignin-rich digested stillage. But for the organosulf, you have a higher fraction of residual weight, I think 0.4 or something, like 40%. So there you can already see like there's an elevated tendency to form solids for very pure lignin. But in our case, the lignin was not so very pure. There might be some residual carbohydrates still there, but nevertheless, you can see that the residual content of solids of the TGA is still significant. So therefore, you can either take this feedstock and do a fast pyrolysis, either you can go for slow pyrolysis. This TGA shows that it's rather fine to choose both of them. However, in the study I'm presenting now, we did some slow pyrolysis, I'm sorry. So you can see there is a block added on the right, on the figure on the right. So after the digestion, where we obtained a digested stillage, we performed some slow pyrolysis to mainly make the biochar here with the retained ash content, and try to see if this biochar is a good biochar to amend in the soil, to have some nutrient recycling, and to have some soil sequestration, carbon sequestration in the soil. The main goal, therefore, was here carbon sequestration and soil amendments. You can also say that you can do fast pyrolysis and have as co-product here the valuable phenolics from lignin pyrolysis, but you would also end up with some significant amounts of biochar which you can still feed or use as soil amendment. This is how the setup look like. It's fairly simple. It's like a small container in which you put your biomass. You heat up slowly with some heating rate. Once you reach your desired temperature, you keep it there for a certain holding time, and then your pyrolysis is stopped, and then you check your biochar. It's fairly simple. And in this study, we tried to use some statistics to optimize biochar yields and some key parameters like the HE ratio and OC ratio. And the things we could change during the process was the highest treatment temperature, which is the process temperature, then the heating rate and the holding time. These are mentioned here. So in essence, or in summary, we were trying to optimize or to play with these parameters to have an optimal char with these optimal HE and OC ratios. So how did experiments typically look like? Well, you have these factors which you can vary over time. You put them at 3 different levels, and then you provide some centerings to be able to do some statistics afterwards. So in summary, this is a table that you would obtain, here pointed here. You have your process temperature ranging from 370 degrees to 450. Your heating rates vary from 5 to 50 degrees per minute, and then your holding times 5 minutes to over 15 minutes to 45 minutes. So you would try to see which of these factors have its most important role in determining the biochar yield and the OC ratio and HE ratio. Now the core results, I have put them into a two-dimensional Van Kevelen part and a 3-dimensional part. First things first, let's check on the left part, the 2-dimensional Van Kevelen diagram. I indicated here your feedstock, which is lignin-rich digested stillage. And you can nicely see, of course, which is logic, that upon pyrolysis, you would end up in this region with a decreased HE ratio and a decreased OC ratio. And in the figure, you have like these dashed lines here. These are the threshold values, let's say, for the IBI and EBC biochar certificate standards. Like, I guess you would all know that the OC ratio should be below 0.4 and the HEC ratio should be below 0.7. So this is then this little square here. And everything within this square is a good char, and everything outside should theoretically not be called a char, but however, right? And by looking at this two-dimensional Van Kevelen diagram, you would already be able to tell something about the charring chemistry. Like if I can give an example, these green dots here are the biochar samples spiralized at 410 degrees. And if you pyrolyze at a slightly higher temperature of 450 degrees, you would see that the OC ratio on the horizontal axis actually does not change anymore. But on the other hand, we have a decreasing hydrogen to carbon ratio. So it would go like vertically down. And this actually means already that going up from 410 degrees to 450 degrees is more or less promoting the dehydrogenation processes. So the release of hydrogen to form these condensed aromatic rings without any significant release of oxygen anymore. So this already tells us something about the charring chemistry as well. And if you then check on the right side panel, this is the same graph, but with the third dimension being the biochar yield here. Then again, logic is coming into place, which tells you that the lower the temperature, the higher the biochar yields, which are the blue points. These are the low temperature, high yield biochars. And the more harsher your temperature, the higher your temperature, the lower your biochar yield becomes. These are the red points. Right. But then, of course, you want to know, or you want to pinpoint the most influencing factor, which determines your char yield as well as your OCS and HE ratio. And to do so, we did some 3 statistical tests, like a simple ANOVA, which is parametric, then a Kruskal-Wallis, which is the non-parametric equivalent, let's say, and also a fancy technique called normality of effects, which I will perhaps explain later in the next slides. All right, so in the table there, here, at the bottom of my slide, I highlighted in the blue boxes the significant factors being the pyrolysis temperature, heating rate, and the holding time. So all these 3 were actually significant according to the ANOVA. But if you then check the non-parametric equivalents, it turned out that this Kruskal-Wallis test only appointed the pyrolysis temperature as a significant factor. So after you are actually, by using this non-parametric test, you're scoping down, or you're narrowing down in a very conservative way your significant factors to only one, here being your pyrolysis temperature. But what about the third test I said? It was a normality of effects test. And let me just quickly explain how this works, because you don't see it very common in literature. It explains itself by looking at the figure below here on the end of my slide. It tells you here all on the horizontal axis, all the factors and its interactions here. Temperature, height, treatment temperature, heating rate, holding time, interaction of 2 parameters, and then the triple interaction. So each of these interactions had an effect on the HC ratio. For instance, if you would increase the highest heating temperature, you would observe a decrease of your HC ratio, right? This is how you should read this figure. Now, you can imagine that you can plot these data points here against a normal distribution. And then you would observe a plot like here on the right-hand side. This is the points of the effects plotted against a normal distribution. And it's, as you know, normal errors on experiments or errors everywhere are typically normally distributed. So non-significant data is typically normally distributed. So if you would have non-meaningful factors or factor interactions, this would only also be normally distributed and fall on this black line here. So for instance, the holding time and heating rate should be regarded as non-influencing factors on the H ratio, while this little fellow here, this highest treatment temperature, is very far from the normal distribution, hence is not error-like, hence is a very significant factor. So what you can do in a very conservative way is to compare all your statistics and take the intersection of all these to have a very conservative estimation on the most influencing factor on your tested properties. So as you can see, I have here my properties being fixed carbon yield, biochar yield, HE ratio, and OC ratio. Then all the relevant significant factors according to ANOVA, Kruskal-Wallis, and normality of effects. And the intersection actually was very consistent, being that only the temperature, the pyrolysis temperature, is saying something real about all these parameters here, which determine your biochar property, quality, let's say. So this is the main conclusion from this part, I would say. If you want to be conservative, only take into account the production temperature. and forget about the heating rate and holding time, because they turn out to be not too influencing for this particular feedstock on the HU ratio and the other parameters. So once you have these factors, you can build models, which I presented here in this particular graphs. And if you have a model, you can predict, and hence you can predict that you have already at this low temperature of 348 degrees, you would already have a compliant char with an H ratio at the thresholds for IBI being 0.7 and an OC ratio below the threshold point being 0.2. And it comes already with a yield of 50%. And people familiar to slow pyrolysis might think that's a very nice result, because at this temperature, you would already have a high biochar yield, which is already complying. And this is quite a nice result here from this particular feedstock. And everything of this result has, of course, to do with the lignin-rich nature, of course. The higher the lignin content, the more charring you would have, so the more char yield you would expect. So this result is actually explained by the 63 class and lignin contents as we've seen before. So that was the part on the lignin-rich digested stillage. Now follows a part on only having digestion and nothing with ethanol fermentation or stillage. Just simply take your waste, take your cocoa waste in this case, have anaerobic digestion, have a digestate from it, and do pyrolysis with it. That's simply what it comes down to in this particular case. And what was interesting to see, we took the elemental composition before the digestion, and we took it after digestion, and we did some calculations and some fittings of data, and we were able to find out, like, to have a common reaction written down in this particular manner. Here. So this is the biomass feedstock, your cocoa, and you digest it to some digestate here in green, with release of biogas rich in methane and carbon dioxide. So in red is the cocoa fresh feedstock, and in green is the digestate. And then by taking the difference, you would see that this is the composition of the digested fraction. Which is nice to see is that this composition of digested fraction here closely resembles that of your carbohydrates. So again, this makes it very clear that if you do a digestion, that your lignin is untouched, and that most of the time your carbohydrates are just converted to your biogas. These are the yields we have here. The yields in your pyrolysis liquids, in biochar and non-condensable gases, upon of your at 350 degrees and 500 degrees. So it shows these two temperatures to do slow pyrolysis. Multiple disclosures are pretty fine. And you can actually see here that the biochar yield did not differ too much. I mean, you go from 50 something, like close to 50 biochar yield for pyrolysis at 350 of the fresh feedstock, to also something like close to 50 here for the digested counterpart. So digestion did not alter too much the biochar yields, but you would have more or less an elevated liquid yield here. It's about plus 6 here percent points for the liquids, and about plus 12 something for percent points for your non-condensable gases. Oh, sorry, it's minus here. So you would decrease your non-condensable gases upon having your digestate and increase your pyrolysis liquids, right? So having it digested makes you have higher yield in liquids. But then here, if you check the composition, the biochar yields might not change, but the composition surely did. It's not because you have same yield in biochar that your composition should also be the same. It was not the case in this particular setup. I have here also a table with the HC ratio and OC ratio for, again, the raw cocoa pot husks, so the raw feedstock, the digested cocoa, and the chars from the undigested parts, and the chars from the digested parts. And you can actually clearly see, if you start from your raw feedstock, an H ratio is, or you have an H ratio, an OC ratio of 0.66. Upon digestion, this decreases to 0.62 because release of carbohydrates, as we have seen. And then if you do some pyrolysis, you would here decrease from 0.66 to 0.32, which is a dramatic decrease, which is nice if you want to have high calorific value char or char fit for soil applications. And you can see the same for your biochar pyrolyzed at 500 degrees. Here, for instance, you go from your digested cocoa char here at 0.62, and the chart counterpart here is in the very bottom, 0.10. So overall, the sequence is clear that you start from a certain waste, you digest it decreases in OC ratio, you do pyrolysis at 350, it decreases again, and then here it should be 500, I'm sorry for the mistake. If you increase the temperature, you would again observe an OC ratio going down again. So this sequence is kind of nice to see. And then now is a slide on the liquids. And I think you should pay really attention to this particular slide because there is much science behind this graph. Explain why. I told you first what you can see on the graph. First, you can see the blue bars are the cocoa pods, which are just raw feedstock at the two temperatures. So this is 350 and 500. And the red bars are those of your digested cocoa. So this is the oil composition of your raw cocoa and digested cocoa, both at 350 and 500 degrees. And something very nice to see is that, something very nice to see is that whenever you did some digestion before, that your composition changes significantly. You would see upon digestion an oil with very few light oxygenates. So with only very few acetic acid and propionic acid and all these type of compounds. And this means that you have, in a way, assured that the quality of your oil also improves. And why? You are enriching your oil in these phenolic compounds. Here you are enriching your oil in the methoxyphenols, methoxyalkyl phenols, alkyl phenols, phenols. All these phenols stay, while the acids, which are stemming from your carbohydrates, are out of your oil because they went to your biogas and they have found their fate in the biogas and not in the oil. So this is something you can see here from this to this lower point. But something even more important to me, at least, this particular compound here, the 2-cyclopentanone derivatives. These are the compounds which also are being derived from cellulose. And I think you can clearly see that if you do pyrolysis at 350 of your undigested feedstock, you would expect some appearance of this particular compounds, because if you do not do digestion, the cellulose in that compound will still find its way into the liquids. And if you increase the temperature to 500, you can see from TGA that all the decomposition of your cellulose is complete. So the degradation compound of this part of the degradation compounds related to cellulose, being this one, would also increase upon the temperature increase. So this is why we go from a full blue bar to an elevated striped blue bar. But something nice to see, this is not happening for your digested cocoa. And why so? Well, because if you have already reduced your cellulose content because cellulose went to the biogas, you would expect little cellulose left in your cocoa digestate. So if you do pyrolysis of your cocoa digestate, only the residual cellulose in there would be deconstructed and would result in this intermediate here, this cyclopentanone derivative. And if you increase it even more, the temperature to 500, there's just simply no cellulose there to convert to this intermediate. So therefore, these red bars are approximately at the same level. And actually, by looking at this chemical composition of your oil, would be able to verify that all the carbohydrates, or virtually all, the carbohydrates being cellulose and hemicellulose, were valorized to your methane and to your biogas, leaving like your lignin-enriched fraction for pyrolysis, and therefore you'd also see that there's a lot of these phenolics here in your oil, which makes your oil actually more valuable to sell or to use as precursor for even pharmaceutical compounds, let's say. So I guess I have said everything I wanted to say on this particular counterpart, on this particular one, which just leaves me with comparing fermentation and digestion with only digestion. So I have broke it down to 1, 2, 3 to 12, 4 bullet points. And the first one is comparing the biochar yield. And what we typically saw was that the biochar yield of the digested sludge is a bit higher than the yield in biochar of your digestate only, which might make sense because your digestate will not be able to convert all the carbohydrates there. So your feedstock of your digestate is not having as much lignin as your digested sludge, and therefore your digested sludge would have a higher biochar yield. It's also obvious in the table here. For instance, for 350 degrees, the cocoa has a yield in biochar of about 50%, while you would have a slightly higher one for digested sludge. And this trend is propagated through for every temperature in this particular table. However, if you compare the OC ratio and AC ratio, there was only little difference there. So the char yield was slightly higher for the digested sludge, but there was little difference between the OC ratio and HV ratio. However, if you check the liquids from both, I have to say there was no liquids analysis done on the digested sludge, but we do have some data for phosphorysis of these feedstocks. And you have here on the right panel a two-dimensional GC plot. From that data, it's however phosphorysis, you can make a ratio. And the ratio would be like you take all the carbohydrate-derived compounds in your oil and divide it over the sum of all phenolics in your oil. And it would tell you a bit how effective the biological pretreatments were in previous processes. So for instance, if you check this ratio of carbohydrates derivatives divided by the phenolics for the raw cocoa pods, you see it's kind of high. It's 1.28. So you have about equal quantities of carbohydrates and phenolics in your oil when you pyrolyze raw cocoa. If you pyrolyze a digested cocoa, if you pyrolyze a digested and fermented feedstock, you would see that these numbers decrease much compared to your raw cocoa, which again comes down to having lower carbohydrates in your oil, having higher fraction of phenolics in your oil. So overall, if I conclude with these last words, overall you would improve your biorefinery output because just simply you're improving your products. You would have your biocomponents being converted to tailored compounds, cellulose tailored conversion to ethanol, hemicellulose tailored conversion to biogas, and phenols tailored conversion to either char or either liquids. And when you would keep these compounds together, you would have more complex oils, you would have more complex chars. So it's kind of a, let's say, valorization through fractionation approach, where you are valorizing your biomass and at the same time obtain a certain fractionation. And this is, I think, a very nice way to handle your feedstock or to handle a certain biomass by which you can create some values. So I guess this was my last slide. And I would say thank you for listening. I have a small announcement to make regarding an upcoming conference, which is held in Belgium, here in Ghent, on pyrolysis. So you might be interested and go check out the website pyro2020.org. All right, thank you, people. I would say it's question time.